table, you redraw the diagram with the states relabeled as letters, as shown here, and the transitions given unique numbers. It does not matter which letters you choose for the states, nor does it matter what numbers you assign to the transitions, as long as both the states and the transitions are labeled uniquely. I would recommend using the states are letters and transitions are numbers convention here, because this makes it very regular in the way it works and compact. So I think that works very, very nicely. So what you can see here in the A row of the zero switch part of the table, we have A1. See that? A1, that corresponds to this guy here. A2, which corresponds to the abandoned, going over here to the E, and then A9, which is that, and that's all of the outbound transitions for the A state. Right? Similarly for B, there's B8 and B10 and B3, so those guys are all here. Yeah. For the C state, we have C14 and C11 and C4. Right, those are all here. And for D, we've got 13, we've got 5, and we've got 12. Those are all there. And then for F, there are only 2 outbound, so there's F6 and F7. Okay? Now, notice that at the end of each one of those zero switches, we are going to be in a state. Now, I haven't specified the state in the table, but you don't need to. It's implicit, right? Once you do A1, for example, you're back in A. You know that because you did A1. Okay? So, now to generate the one switch side of the table. Basically, because the maximum number of outbound transitions is 3 from any given state, in this particular example, the one switch part of the table needs 3 squared columns, right? Because if we leave a state that has 3 possible outbounds and we land in a state that has 3 possible outbounds, then the maximum number of combinations there across those is 9, 3 times 3. Okay? So what I've done here is I've broken this up. I've got 9 columns, and I've broken it up into some nice groups of 3, each one corresponding to where I land from the initial starting zero switch. Okay, so take a look. A1. The first 3 here correspond to the different things that could happen with A1. Okay, so I could go A1, A1. That's 2 transitions long, and there it is. Or I could go A1, A2. Right, 2 transitions long. There it is. I could go A1, A9. That's that. Now A2, be nice and regular here. A2 drops me into E, and nothing can leave from there, so there are no one switch entries in the one switch side of the table that correspond to the A2 column in the zero switch side. See? Because once I get into E, there's no outbound. Therefore, there's no sequence of transitions of length 2 that starts with A2. A9 is a different story. A9 drops me into B. Okay? So, what happens when I drop into B? Well, let's see. I already know, actually, what happens when I drop into B. I don't even have to go through it again as I did here. So I go, okay, A9 drops me into B. Okay, well, what are the zero switches associated with B? Well, it's B10, B8, B3. B10, B8, B3. See how regular that is? You just have to figure out where where the zero switch is going to drop you, and in terms of state, and then you look at the zero switch row corresponding to that state, and you create the possible combinations there. So similarly, Here's the B row, and I got B10. Now B10 drops me into C, so there's C14, C11, and C4. So there they all are, right there, right? B10, C14, B10, C11, B10, C4. B8 drops me back into A, so there's A1, A2, A9. There they all are. B3 drops me into E. There are no outbounds from E. Okay? So everybody see how to generate this table, I hope. It's a purely mechanical thing, right? Looks complicated at first, but once you see how the zero switches are created and then how the one switch portion is created from the zero switch side, it's purely mechanical. Now, obviously, it would not be a lot of fun for a complex system that had a lot of outbound transitions from it, right? So, but if you want to try to force simple systems to have long length transitions, and that's something you can do with this technique. Or better yet, just figure out a way to automate it. Okay, so to derive tests that achieve a certain level of switch coverage, what you want to do, again, start with the tests that you derived from state transition, from the state transition diagram for state transition coverage. Don't go back to the table. The table, once you've done the table to try to force out into the open those unhandled events or event condition combinations, that you don't go back to it. Okay, so start with the tests for state transition coverage and then construct the switch table. Confirm that the tests that you already had cover the zero switch columns. And of course they should, right? Because our coverage criteria for the state diagram was visit every state and traverse every transition. So if we've traversed every transition, then certainly every transition sequence of length 1 should have been traversed at least once, right? Now, what will typically happen is that not only will you have traversed all transitions once, because most of the tests that you define will end up being more than one transition long, you actually have covered higher order switches. Now, in this case, we're only interested in one switches, in other words, transitions of length 2. But you typically will have covered sequences that are 2, 3, 4, maybe even 5 transitions long in the course of a single test. Okay? So check to see what you've already covered. Then look at your 1 switches, 2 switches, 3 switches, whatever, however high you're going with this thing, that have not been covered. And take a test, again, existing test, or just use zero switch sequences to get you to a state where there is an uncovered higher order switch starting. Put that switch in the test, repeat until you get to a terminating state. Again, mark the switches covered. So you got the table, highlight them, you covered them. Repeat that until done. Okay, so let's take a look. The 5 tests that had been previously defined for state transition cover are shown in the blue highlighting here. Okay, so you see we did get all of the zero switches, plus we got a bunch of the 1 switches. See that? Just by tracing through the 5 existing tests. But there were some that we didn't get. Okay? So the red shaded cells are new ones. So we did not get A1, and we